Okay, in this video, we're going to look at some more examples and talk more about NMR because I know that you're enjoying it so much. I'm going to give you more and more and more and more of it so that way you'll be totally happy by the end of this semester. So this problem actually is a different take on what we've already been doing. So it says, how could you distinguish between the H and MR of the following compounds? And it gives me A, B, and C. So if we have these three compounds and we analyze them in an NMR, how can we determine which one is which? How can we play match game with these, right? That's what this is really all about. So this is going to kind of relate to the whole, how many signals do we have in the following type of example problems that we've done over and over up to this point. So if I take a look at the choices that they give me, based on what I know right now, and there's very limited what I know right now of NMR, it's just the number of total signals. Let's see if this will actually help us determine which one is which. So if I look at A, it looks like CH3 group, ding ding, I get a signal. And then a CH2 group, I already know, ding ding, it's a signal because there's two hydrogens here and there's three hydrogens there. And then if I take a look at the ending CH3 group, that is actually the same as the first one, right? So they're very symmetrical here. So A would actually give us two signals in total. This CH3 group is on an O, this CH3 group is on an O, and each one of those O's are on the CH2 group. It's the same no matter if you go forward or backward. Don't believe me? The hydrogen, replace it with a bromine, and you'll see it's the same name. For B, we actually see, ding ding, a signal here, and then it's actually the same signal to the right-hand side. That's also a CH3 group on an O. This is a CH3 group on an O. It's a very symmetrical molecule, so we will only see one signal from there. So far, this looks pretty good, right? A is going to give me two signals. B will give me one signal. Now let's see what C is going to tell us. So if I look at C, this CH3 group, ding ding, it gives me a signal. And then we have a CH2 group that's different than that CH3. So of course that's going to be a ding ding. So we get a signal there. This carbon doesn't have any hydrogens. It's got a methyl group up there and a methyl group down here. Those three methyl groups are actually identical to each other, but they are different than the CH3 group that we already have, right? So this is going to be another ding ding up here, but only one because the one at the bottom is going to be the same. Then we go to another CH2 group. This CH2 group, we also have a CH2 group to the left. Are they the same or are they different? Well, this CH2 has a carbon attached to two methyls and an oxygen as neighbors. And this CH2 group to the left has a carbon with two methyls and an oxygen as neighbors. So it looks like this would be the same signal. We've already taken care of that one. Very symmetrical here in the middle. And then the ending CH3 group, this is on an O with a CH2, and this CH3 group that we started with is on an O with a CH2. So those, again, are equivalent. So it looks like that particular molecule will give me three signals, unlike the first one, which is two signals, and the second one, which is one signal. So that's how we could distinguish between the H and MR of the following. Okay? All right, so that just kind of rehashes everything that we've learned about in the past couple of videos. And now I want to go a little bit further into the mechanics of NMR and why it works the way that it does in a way. So one of the biggest, kind of most important pieces of information here is that just like an analytical balance in a laboratory, we have to what we call tear out the NMR. So when I go to an analytical balance, I hit the tear button, it's going to give me a display that reads 0.0000, right? So we're going to have to do the same thing with NMR. We're going to have to give it a standard, and this standard is going to tear it and make it read 0. That is the purpose of this particular type of molecule that we're going to be using. So as with many of the instruments that are out there in an analytical world, we have to have something to make this instrument read 0 with in order to blank it. And what we use in the world of NMR is something called TMS, all right? So the T is going to stand for tetra. The M is going to stand for methyl, and the S is going to stand for silane. So tetramethyl-silane. This TMS has a really low boiling point, all right? That is one of the benefits that we actually get from this compound. It's 26 degrees Celsius. So this is just a little bit warmer than room temperature. You could probably cusp it in your hand, and the heat from your hands will probably warm it up enough for it to evaporate right in front of you. That's all that we really need. And this is good because we can actually evaporate this solvent from the sample very easily. And that is why this is so great, right? One of the benefits from TMS. So if I'm going to tear out the instrument, I can actually put TMS in the machine and tear it. And I can also put TMS in my samples as well. And that TMS at the end of this analysis can simply just be a little bit of heat. That's all that I'll need. And that a little bit of heat will be enough to drive off all the TMS that I have injected into my sample, leaving my sample undisturbed behind. I probably have not heated it up that much. I've not lost it. I've not gotten close to the boiling point of the compounds that I'm trying to actually analyze. And that is what TMS really does have going for it. So TMS is going to, excuse me, TMS is going to be the reference of choice here as far as the signals and the zeroing or the blank of the machine goes. So as far as TMS is concerned, tetramethylsilane, that basically means that we have a SI in the center, and tetra means 4, and it's 4 methyl groups, tetramethyl, right? So this is the structure of TMS that we use in the world of NMR. A little bit of this is injected into the actual sample, and this really on the software or the computer screen or the spectrum begins my 0 mark. And this 0 mark is going to be 0 as far as concentration is going to be concerned. And this is really setting the starting line here. That's what I like to call it. And these terms are going to be in units of part per million. That's what really all of this is about. So that is the unit that typically goes on the x-axis as far as the NMR spectra is concerned. Now, why is TMS chosen? Because, you know, there's a lot of things out there that have really low boiling points that we don't really have to choose this one. If it's just boiling point related, why aren't we doing something else? Well, first off, the other good things that tetramethylsilane actually has going for it is, number one, it has hydrogens, okay? And these are equivalent hydrogens to each other. If you've noticed, they're a very symmetrical molecule here. Silicon is in the actually middle, and then around the outsides, we have all CH3 groups. So they are equivalent to each other. So we're not busying up the signal. We're keeping it very simple. And then in addition to that, we also have a very low boiling point compound that can be driven off with just a little bit of heat. However, another reason that we do TMS is because if you look in the center, there's not a carbon here. It's a silicon atom, right? Si. So this Si is actually less electronegative than carbon. And what this means is that we are guaranteeing that this is the furthest to the right on the NMR spectra. This really is the 0, because what you're going to find out is that on the NMR spectra, 0 does not start to the left like a normal calibration curve would. 0 starts all the way over to the right-hand side, and it works backward from there. So this TMS allows me to ensure that this is the furthest to the right, and that is exactly what we need in the NMR. I don't want to pick something that I'm going to blank my compound with, and that actually might not be the lowest signal possible. Maybe my sample is lower than that. So we are ensuring that we are the lowest by playing off of electronegativity values, because you'll see why in a couple of videos from now. But those really lower electronegativity values than carbon helps TMS ensure that it's to the right of the NMR spectra, and that's exactly where we need it to be. All right. Not only that, but the signals are also very weak. So when we do get signals from the NMR, this is going to be so tiny. They're going to be present. I'm going to be able to see them, but they are so little that it's not going to distort the NMR in any certain way at all. And that's actually pretty good for us, right? We don't want something so tall that it just distorts the entire NMR, and I really don't see signal from the actual sample. All right. So this is basically what we use in the very beginning when we run samples on the NMR, and then we add this to all of those samples that we run on NMR, and after that we get this NMR spectra that we will eventually start looking at from that point on. Okay. There's also some terminology that I want to cover before we go further into the NMR field. And the first one is something called a chemical shift. So a chemical shift is really what we are referring to as the signal. Okay, that is the line that we're going to be seeing on the NMR. So let's say that we have an NMR. I'm not going to pick it apart, not quite yet, but let's say that we have a 0 mark here at 0 ppm. That's where my TMS is going to be. And let's say that we have a signal. It looks almost like a mass spectrum in a way. So we just see a line that shows up. And this particular line, we don't call it a line, we call it a chemical shift. So that is in regards to the signal. So just some proper terminology that we use in the world of NMR. So each shift, that's what we call it again, corresponds to how far the shift is from the reference signal. So there's going to be a value or a number down here at the bottom. These values are in regards to how far away it is from the signal of the standard, which is TMS. And again, these values are going to be in the ppm. Now, in the beginning with NMR, especially in a textbook, they're going to tell you the most common scale for chemical shifts is the delta scale. So the squiggly D, and they call it the delta scale. This delta scale is great. I mean, it's something that we can talk about. It's something that I can refer to, but no one in the actual industry uses the delta scale. Instead, they use parts per million. That's how we measure shifts. So the chemical shift is determined by measuring that distance, right, between the TMS and this number that we are referring to. This is a delta scale, but actually, I've already told you, NMR is very similar to a radio frequency, and this can be measured in terms of hertz. So we can measure the distance from TMS by using hertz as a unit. And if we divide that by the operating frequency, which is megahertz, then we can convert into a unit of hertz over megahertz, which actually breaks down to a simplified unit of part per million. Mega, look at how many zeros there are present. So that is 1 hertz for every megahertz. And that, in other terms, in other definitions, is also called parts per million. All right. So this is how far it is from the TMS signal. And this is what we would call the operating frequency of the actual instrument, of the NMR machine. Okay. The numbers that we see typically down here on the bottom, 0 normally starts over here on the right hand side, and we normally go to 12. You know, it can go a little bit further than that, but on a normal working NMR that we will see, that we will interpret from here on out, that's just the normal kind of working range for analysts that might take a look at this type of data. It really just kind of stops at 12, and it doesn't really go any further. Keep in mind it can, but 0 to 12 is the typical working axis on the x-axis of the NMR spectras. Okay? All right, so parts per million's the unit. 2 part per million, 12 part per million, 6 part per million, 0 part per million. But keep in mind that part per million is actually in reference to the hertz, which is the distance from the TMS to the signal, over the megahertz, which is the operating frequency of the instrument. Okay? All right, so I think I want to show you an actual image of an NMR at this point. So let me pull one up and we'll start to pick it apart. Okay, so what you see on the computer screen now is an image of a real NMR, and notice it's nothing like a lot going on here, right? It looks like my axis here at the x-axis, again, the 0 mark is here, and I see a very tiny signal right there, and that's from the TMS, which is good again, and that gives me my starting point. That is my tare function, and then it looks like there's kind of a line that jets all the way up and then it comes all the way back down. So it looks like I have a chemical shift that is right here around a 1 part per million, and then it also looks like I have another chemical shift that's here, and that's like a 3.4 or 3.3 part per million, somewhere in there. And then it doesn't look like I'm seeing any other signals at all coming from this substance that we ran. Just 2 lines that shoot straight up, one at a little more than 1 and one at about a 3.3-ish. So I want to kind of connect the points now, connect the dots. And these chemical shifts are in terms of the signals that we have talked about in previous videos. So if you go back and you take a look at all of these example problems that we did, looking at the number of signals from the compound, this is really what we're referring to. These are the signals that will show up on the NMR. So for instance, here is the molecular structure for what you're seeing on the image. So if I take a look at this problem and I say, how many signals would you get from the following compound? Well, you would look at this and you would say, ding, ding, right there. That's a CH2 group connected to a bromine. And that CH2 group automatically is going to be different than the CH3 groups, right? Because there are a different number of hydrogens. It's automatically different. So then we're going to find another ding, ding that's going to be here at the CH3 group. But that CH3 group is equivalent to the one to the left, and that's equivalent to the one at the very bottom. They are all connected to the same carbon. So they're all 3 the same equivalent set of 3 hydrogens, which means that this signal is going to be in reference to 3 plus 3 plus 3. That's 9 hydrogens in total. Where this carbon and that signal with those hydrogens, that's representative of only 2 hydrogens that we're getting from that. All right, so 2 signals is what we would have said in that example problem. And folks, here we go. There is signal 1 and here is signal 2. So that is how we're going to start relating all of this information together. All right. So now we're going to take a look at another type of example problem that starts to relate this information together. And this example problem says, how many hertz downfield from the TMS signal would the signal occurring at 1 ppm in a 300 megahertz and a 500 megahertz spectrometer? So this is the idea that different NMRs are made in different ways, of course, right? That's one of the reasons that they're different. And sometimes we're applying a stronger magnetic field onto these molecules than other times. So it really depends on what I'm using, what I'm doing, what type of instrument that I have. And depending on that machine, the signal that I'm seeing from these could slightly be different. So we're looking at distances. How far away from the TMS would I see this signal show up if I begin to change the operating frequency of the NMR? So we first have a 300 and then a 500 spectrometer. And it does tell me a 1 ppm, right? All right, so the way that we would solve this type of example problem is that this instrument, keep in mind, is ppm. So this is hertz over this megahertz number, which is the operating frequency of the instrument. All right, so in the first example, it tells me Well, you've got a 300 megahertz, right? All right, so a 300 megahertz is actually going to go there at that spot. So this is a 1 ppm. That's really what we're after. That's what the problem says, right? So it says how many hertz downfield from the TMS signal would the signal occurring at 1 ppm in a 300 megahertz spectrometer. So a 100 ppm or a 1 ppm is going to go there. And we need to solve for hertz here. All right, so if I take a look at this problem, it seems to me like we've got this 1 ppm and we've got this 300 megahertz and we have this other number that is a hertz number. So if I asked you to solve for hertz, you would look at this and you would say, well, it looks like a 300 times a 1 is a 300, and that's equal to x, and x is equal to the hertz that's associated with that value. All right, so what that means is that at 300 hertz, we would see the signal, and that would be in a 300 megahertz operating frequency. If you take the 300 divided by 300, you will end up with a 1, okay? A 1 part per million, and that's what that problem said. So if the problem said, all right, well, what if it's not a 1 ppm? What if it's a 4 ppm? That's not a big deal. I'll put a 4 there in that spot. So if this is the 4 ppm value, and I see the 300 here, well, then I'm going to take 300 times 4, and that will give me 1200 instead. So 1200 would go up on top, and we would see 300 at the bottom. The next part of the problem, part B, said, well, what if it was at a 500 megahertz? Not a big issue. The 500 would get replaced here at the bottom, and then I would keep the 1 because that's how the problem was originally stated. So I would take 1 times 500, and that would be 500 hertz at the 500 megahertz, and that would give me a 1 ppm. So that's how we would solve these ppm problems if they do ask them. But to be honest with you, very few times will they ask questions like this one, right? And the reason is because they're more focused on what the NMR spectra is actually telling you than anything else. Okay, so that's a little bit of TMS, the point of tearing the instrument with my blank, and that's basically the TMS solution, and an introduction into what NMR spectra is going to look like. And these peaks representing the signals that we've already had plenty of practice with in determining in molecules. Okay, so in the next video, we'll continue with terminology, and we'll start talking about the different areas of this NMR chart that you're seeing on the screen.